we will be talking about Lincheck again. Probably. Do you have you answered already all the questions during their break? There were some of them.
Yes, I think
Maria?
so. And Nikita Koval also came to help us.
Yay. That's cool.
Okay, so if there is no questions left, let's probably try to start then. Maria, please continue with the progress guarantees. Probably you can explain to other viewers what is program guarantee is, but I guess everybody should know that. Otherwise, they will not come to this conference.
Okay. Thank you, Vitaly. So let's move on with our talk. Till this moment, we've discussed how we can configure the concurrent execution scenario and what strategies are available to run it. And we've mostly talked about the correctness guarantee. And now we are talking about the other functionality of Lincheck. That it's a common problem when you need to check your algorithm for progress guarantees. It's a non-trivial task because you don't need to have explicit synchronization in your algorithm so that it would be blocking. And here Lincheck can help us. We can check our algorithm for obstruction freedom violation. I guess many of you don't know what's obstruction freedom, and I will explain it to you in the next slides. We can use Lincheck can test the algorithm for progress guarantees in the model checking mode that we are already familiar with. Maybe my story about how model checking works under the hood was a little bit messy, and you didn't get any details. But here is how we can use this strategy to check for progress guarantees. While Lincheck is exploring all potential switch points at the current level, it tries to complete all operations since from the chosen point, and if it stucks in some infinite active loop or in some synchronization, that means that our algorithm is blocking. That's exactly what obstruction freedom is. Obstruction freedom states that any operation should be completed in a bounded number of steps if all other threads are stopped. And in model checking, that is exactly what we are doing. So we do not execute other threads. We are now trying to complete execution of thread 1. Thread 2 is stopped. And we found a blocking point in our algorithm, so that is a progress guarantee violation. Maybe obstruction freedom is not the progress guarantee you've heard about, but maybe you've heard about lock freedom and wait freedom, and obstruction freedom is the weakest guarantee of those. But very often obstruction freedom is enough because many bugs are reviewed when there is a blocking code in our algorithm. So to get this idea how an algorithm without explicit synchronization may be blocking, I suggest you to perform a task that is located at the branch of 5.1 data holder. You can check out this branch in your project again. And there you have, let me open it.
Yeah. Ladies and gentlemen, Dr. Morris Herrliche.
Oh my God. Okay, so let me open let me open this branch with you. So we go to this branch, and in main package you see a lot of code, but what was this algorithm is about? Here we have some data holder that holds two values, first and second, and we want to write these values simultaneously, but we're not going to use any locks for that. Instead, we use some versions to make these writes, to make reading and writing to these values atomic. We can, as you can see, there are no any active synchronization in this algorithm, and we are going to check whether this algorithm is blocking or not. How we can do this? If you maybe you have forgotten what is the option for this check. I have returned this slide to you. So when you write the model check-in test, you can provide an option that is called check abstraction freedom, and this option allows you to check the algorithm for progress guarantees. Please set this option and check the algorithm provided for whether it's blocking or not. If you do not set this option and just run the test now, just run the model test on the algorithm, it will successfully pass because our algorithm with versions for the non-atomic data provided us the atomicity that we wanted. So now we are going to check it for progress guarantees. Dmitry, could you please tell me, is this a common problem when you want to check an algorithm for whether it's blocking or not? And other many tasks in practice when you write algorithms without explicit synchronization, like synchronized blocks and locks, and want to know whether your algorithm is blocking.
Well, it's obviously is actual problem because most of the time when you try to implement some lock-free algorithm, you have suspicious thinking that maybe it can stuck somewhere. Usually you are hoping for lock freedom, but it's less easy to check. But abstraction freedom is mostly the good option for verification.
And that's a often task to write lock-free algorithms, because we are going to talk about lock-free algorithms in the next part, and I'd like to know whether it's a practical issue or not.
Well, I think that generally lock-free algorithms are not so often to implement because it's very hard, and most programmers just use some ready-to-use libraries, and that's a common wisdom. But when you're working for high-performance scenarios like low latency trading or something like this, you often need some specialized queues, some modification of general classic algorithms with some teeny improvements. So in such a high load scenario, it may be needed.
Okay, that's
it's dangerous, but it pays for itself when it works.
Okay, that's good that we are not talking about some theoretical things in the bubble, and some people may still need this. So let's return to our task again. I guess you have set this option in the data holder test. Let's run this test now. Are there any problems in the chat? No. Yeah, I guess no.
There is no problems
No
with
problems.
the chat.
But
Questions.
Well, just questions. Do we have any questions according to these to the current test?
Not really. Everybody is fine.
Everybody is fine and asking simple questions about the previous sections, right? Yeah.
Yeah, you can ask a simple question. Yeah.
No. Okay. Okay. I'll answer all your simple questions in the question section. And now let's proceed with the result. What we get here, there was in the first part there was a problem that some people had trouble reading the Lincheck output. So let's stop here in more details. So we ran the model check-in test for the data holder, and it failed. And the error says that abstraction freedom was violated. And as we used model check-in mode, we got the trace that shows us how exactly algorithm is blocking. So what happened? We ran two operations in parallel. In the first thread performed the write operation, where we decided to write -4 to the first field, to the field called first, and -8 to the field called second. And in parallel, we tried to read those values. The execution started from the first thread. The write operation started, and the version was read. According to the algorithm, we at first increment before writing to our fields. We increment the version. That states the start of the write operation, and we see that we performed the version write instruction. Then this point in the thread was a switch point, and we switched our execution to the second thread. The second thread started to perform a read operation, and here we see the infinite invocation of version read. What has happened? If you look at the implementation of read operation in the data holder class, you'll see that we are reading in a loop version. We are reading version value in a loop, and till it equals 1, we wait because that means that there is a concurrent update of the value, and we do not start to read first and second values until concurrent write is finished. And so here we are stuck, and the Lincheck found the active loop and reported about progress violation, and that's exactly what we wanted. That's exactly the problem. So you see, our algorithm did not have any active synchronization or locks, but it still fails. It's still blocking. Now let's move further in this topic and talk more about.
Excuse me, may I?
Yes.
Ask a question for myself. You said that it's infinitely looping in the second thread, but what does it mean infinitely?
Not
does
infinitely,
it
but
know
just
what it's? Okay, so it's limited for some number of repeating. Is it a parameter of
yes, yeah. That's a parameter of this option of check abstraction freedom. If we are stuck in some place for some iterations, that means that we have a blocking loop, and something is not okay.
Okay.
Yeah, that's an option. So let's move forward with the topic of progress guarantees. And now I want to tell you about some. I don't want to tell you about some complicated log-free algorithms, but rather I want to tell you about the common pattern that is used in log-free algorithms. On the example of the most common and simple log-free algorithm that is used almost everywhere in every language, that is Michael Scott log-free queue algorithm. In Java standard library, it's concurrent. It's implemented in concurrent linked queue. Here I'd like to tell you about the pattern of helping in log-free algorithms. Let's just make a quick recap of how the Michael Scott queue works. So initially, it is represented with a list that consists of one dummy node, and both head and tail pointer are set to this dummy node. Then when we enqueue a node to the queue, it is placed to the tail of the queue, and when we perform dequeue, the node is removed from the head of the queue. But we are not interested in dequeue. Let's just pay our attention at the enqueue function. Like in most of log-free algorithms, our enqueue operation will consist of two parts. At first, we want to set the next pointer of a node to the new node, and then we want to move the tail pointer itself. So let's see how it happens. For example, we want thread 1 to perform operation to enqueue node 5 into the queue. So this thread creates a node and then tries to at first cast the next pointer of tail to this node, and this is performed successfully, no problems. And then it may happen so that thread 1 suspends for some time. There comes thread 2 that also wants to perform enqueue of let's say node 7, and it does exactly the same. It tries to perform cast of tail is still on node 1, and the second thread tries to perform cast from the current the cast of next pointer to the new node, but it cannot succeed because this pointer has already been set by the first thread to the node 5, and cast fails. This means, according to our algorithm of enqueue, that the second thread should wait in a loop, wait for thread 1 complete its operation, and here we again come to the blocking algorithm. So thread 2 may loop here infinitely, and no one will help him. So and here we come to that common pattern that I've told you about. In log-free algorithms, it's a common practice to when threads help each other. So I say here that thread 2 can help the first thread that suspended to complete its operation. So if the second thread first helps the first thread to move the tail pointer to the node 5, and then continues with its operation, then everything will be okay, and no blocking will occur. So now, when the second thread helped the first thread to complete the enqueue operation, and the tail pointer is set on node 5, then the second thread can successfully continue with its enqueue, and no blocking will occur. We can see this. I have placed this example with the microscope queue in the branch 5.2 microscope queue. You can check out to this branch, and in the main package you can find the file microscope queue that contains the log-free algorithm itself. And now, so I check out here, and in the microscope queue file from the main package, you see the algorithm that I showed you on the slide, with this helping operation commented for now. So it can still be commented, and you can write the test in the microscope queue test. It contains that check for abstraction freedom option that checks the algorithm for log freedom, for abstraction freedom, I'm sorry, and ensure that it fails. It fails with the exact scenario that I've told you on the slides. So there are two. If you run the test, you'll see that the problem occurred when there were two parallel enqueue operations. The first thread started the execution, and then so it started its operation and performed pass on the next pointer of the tail, and then switched the execution to the first thread, and then the first thread just waited in a loop while the next pointer was not null. It could not proceed with its operation. And you can also ensure that everything will be okay if we run the test with helping. The test will successfully pass and no blocking will be found. So I've shown you this example, not because you are you don't know what microscope queue is, but to show you that it's a common error. It may be a common error to forget this helping operation. Then your algorithm will still be correct. Will still be correct, and will not fail maybe on different scenarios. But it will be blocking in some. It will be blocking for some interleaving, and that may be a crucial issue in your case. So, Dmitry, do you have some comments on this section? Because I guess that's all I wanted to say about progress guarantees. Maybe you have some practical cases where we can apply this option of Lincheck.
Well, actually, if you expect that algorithm should be log-free, you always should use this option because it's the best what we can check. Log-free would be even better, but it's harder to test.
Yeah.
So actually, in practice, abstraction freedom in most of the time is enough because somehow interleaving on the hardware level just forces it's not to stuck forever. But in the practice, sometimes we have a real manifestation of non-low freedoms of the algorithm because we used a special scheduler for high performance in the Linux, and it's never switched to the low performance state because high performance state was formally runnable.
Okay, so if we don't have any problems here, don't have any technical problems here, we can move forward. And the next very useful feature of Lincheck is modular testing. Sometimes when you write a complex concurrent algorithm, you may use some linearizable data structures as building blocks for your algorithm, and then testing may become a real problem because you have a huge number of different interleavings while using other data structures. And if you know that those data structures are correct and linearizable, we can add guarantees that methods on those data structures are atomic. So what does it mean internally? Lincheck will not set any context switch points inside those operations. So we will consider them correct and atomic. To see how this feature maybe how it works and that it may be really useful, I suggest you to go to the next branch that is called 6.1 multi-map. I'll go there too. Why? So in the main package. Oh, I have conflicts again. Sorry. In the main package, you see the implementation of multi-map. Why it's multi-map? Because it's just a concurrent. It's just a concurrent hash map from some key to the list of values. That's why it's multi-map. And I have implemented addition to the list corresponding to addition of the element to the list corresponding to some key. There are two implementations actually. Add broken, as you may see by its name, it's not correct, and the correct implementation that is called add. Here what I want to show you is using this model checking feature. So please, we see here that we use concurrent hash map on the back of our multi-map. We know that concurrent hash map from the Java util concurrent package is linearizable and does not have bugs. So we may rely on its operations and guarantee that they are atomic. So please, add guarantees on these. Add guarantees on the atomicity of concurrent hash map in the options of model checking options of the test, and is run the test. Run the test and see what happens. Here we are expecting an error because we are testing concurrent execution of add broken and get operation. Please run it, and I give you some time here. I give you some time here, and well. So this is how the result should look like. This is how the result should look like. We just added the guarantee that all operations, all methods of concurrent hash map are atomic, and we run this test. We run this test, and it fails. It should fail sometime. Yep, this test failed. This test failed, and you may see the output. You may see the output here. If we what happened? I guess the color of my screen turned to night shift. That's trouble. I should fix that. Okay. Now it should be better. Yep. We are back to the white screen again. If we for this test, we can comment this add guarantee line, and run the test without adding guarantees for concurrent hash map, and run the test again. And it does not take a lot of time for it to find a bug without adding any atomic guarantees. So you may ask here, although it runs a little bit longer, but still it fails. We found the same bug without adding guarantees. So you may ask here why we need this option at all. If model checking is good enough to check all interleavings without skipping operations of correct data structures. And I can demonstrate you why we still need this option. Imagine that we have the problem here was that we tested concurrent execution of add broken method and get method. Add broken had a rather obvious bug, so we did not have so model checking mode did not have to analyze many interleavings to reveal this bug. But imagine if our data structure is correct. Our data structure is correct, and we are running the test to ensure that everything is okay. So we are likely to check all possible interleavings. We say, as I have told you in the first part of our workshop, we in model checking mode we bound the number of interleavings to cover. So let's set the maximum bound possible and ask Lincheck to analyze all possible interleavings and set its number to integer max value. And now, so our data structure is correct, and we are going to run a model checking test. We are going to run a model checking test on the correct data structure and analyze all possible interleavings. Let's run this test. So now Lincheck tries to set switch points everywhere, even inside methods of the concurrent hash map. And that's an enormous amount of context switches. That is really space consuming, space and time consuming. So we are waiting for this test. And spoiler, it should fail with the lack of memory, with Java out of memory error, or that there is not enough heap space. We can wait till then. Yes. I want to show you that we need this. We need these features. So, Dmitry, do you think that this is a useful feature? So that we could this feature that optimizes the testing.
Yes, obviously. Actually, that's always the problem with many academic tools missing some technical features like this, and it's hard to apply to some non-trivial algorithm because of that.
So I guess we cannot wait. We cannot wait for this test to run longer, because you see, it will fail. It will fail with the Java out of memory error. My test is still running. Your test may have already failed with some error, but you will not model checking will not model checking, but your machine will not be able to analyze all interleavings, though the algorithm is rather simple. And we kill this test. It ran for quite a long time. We add this guarantee for concurrent hash map methods back and run this test again. So we want to check all interleavings, all possible interleavings of our algorithm. And now we should end in a finite. This test should end in a finite time. Okay. Oh, there are some questions about internals in the chat yet. Yes. So this test will eventually pass. I don't know, but yes, the test has passed, and that means that we have checked all possible interleavings of our algorithm, and yes, using this guarantee. So that was rather useful, I guess, and we can move forward with the presentation. And now we are going to the part that you have already asked in the chat. How we generated some concurrent execution scenario, and we ran it using some testing strategy, and got some results. Now we are going to discuss how we know whether these results are correct or not. The simplest solution for the verification problem would be to generate all possible sequential histories of our concurrent execution scenario, execute them, and see whether there is one that produces the same results as we got during concurrent execution. But that would be a very space and time consuming solution, not effective at all. And we have solved this problem. We are building a graph. We are building a graph of sequential histories that is called LTS, like a labeled transition system. What is a labeled transition system? It's just a graph where nodes are states of the data structure that we are testing. In this example on the slide, that is a counter, and edges of this graph are marked with operations, and the corresponding results that we get when we invoke this operation on the state of a data structure. So we see here when we start from initial state, and perform increment. Okay, here increment returns the old value, so it returns 0 and etc. Yes, here is what LTS is. We're now going to look at a more practical example. So imagine now we are going to follow step by step how verification is performed inside Lincheck. So imagine that you have some queue, some concurrent queue. Lincheck generated the following concurrent scenario for this queue, and executed it using either stress or model checking strategy. And we got the following results. Now we need to verify these results. We need to say whether these results are possible in the linearizable execution. So we start from the initial state of the queue and try to lazily build this label transition graph. We try to execute the operation from the first thread. We execute operation add, and from the initial state of the empty queue, we go to the queue that consists of the single element, and that is 4. Everything is okay for now. We executed add operation, it returned void, and the result is void. Everything is fine. Then we try to proceed. We are trying to find some sequential execution. So let's try to proceed with the execution of the first thread and execute poll method on this new state of the queue 4. But when we execute poll operation, we got 4. And that is not the result that we expect and that we have got during the concurrent execution. There we expected 9. So from this thread, from this state, we cannot poll that returned 9 was not the operation that was executed next during the concurrent execution. So then we do not proceed with the execution of the first thread and switch to the second thread and try to execute add operation from the state 4. Everything is fine, and we get to the next state of the queue. Then we return to the first thread again and try to execute poll operation again. But we still get the wrong result, and that is not the operation that came next. So we again try to execute the next operation from the second thread, and now there is success because now the poll operation returns 4. That is the exact result that we expect. So we can move forward. And the last operation that is left in the scenario is that poll that we have already tried to execute 4 times. And now it matches the result. Matches, that is success. That means that we have found the sequential execution, that returned the results that we expected. Yes. So we started from thread 1, then we switched to the second thread, completed it to the end, and switched to the thread 1 again. So this execution was linearizable. Here we have, if you have some questions here, please ask them. Okay, let's move forward with some practical features of verification. When you run all tests, the tests from all the tasks that I've given you, at the beginning of every output, you saw the annoying warning that started with the suggestion to make your verification faster. So what does it mean? What does it mean? It means that, as I've shown you, I've just shown you the process of building the LTS, and you may have noticed that we do not create states that on the picture that I've shown you. We did not create new states if there are equal states in the LTS already. So, for example, if we start from the empty queue and then perform add operation on this queue and then call poll operation, the queue will become empty again, and we already have this. State in the graph, so we can reuse it. But we can reuse states if we have defined state equivalency relation on them. you can define a state equivalency relation via setting equals, and we are implementing equals and hash code methods on the data structure that you are testing. But there is a more convenient way to do this. You can just extend the verifier state class and implement the extract state function. Why it's more convenient? Because implementation of extract state may break your data structure, can modify your data structure. Because this method is called once for every object during verification, so that will be okay. So what is the profit of implementing this extract state function? Then you can, if you implement the extract state function, then it means that you set the state equivalency relation among the states in the graph. That means that you will reuse the states in the graph, and if you reuse the states of the graph, it will be more effective. You will consume less memory during verification, and it will be faster. So that is the first point. That is the first point with verification. One more thing that I would like to tell you in this topic is setting sequential specification of a data structure. Why do we need this? Very often, when you write a concurrent algorithm, you are not even sure that it works correctly in the during the sequential execution, that it satisfies the sequential semantics. So you may provide a sequential execution. So you may provide this sequential semantics, and if you set it this way, like is shown on the first piece of code, if you set this sequential execution in the options of your test, then Lincheck will automatically check your concurrent implementation for satisfying the sequential specification, and this same sequential specification will be used to build the verification graph. So every time you make a transition from one state to another, the method on this sequential specification will be called. This means that if you want to set state equivalency now, you should provide it for the sequential specification, because that it is sequential specification that will be used to build the verification graph. I'm going to suggest you a task for these two features, on verification. Please go to branch 7.1 verification. There you will find the queue. I guess the queue from GCTools library that you've already seen in some task for setting constraints. That is a multi-consumer single producer queue, multiple producer single consumer queue. And now we are going to, I ask you to set the sequential specification for this queue. And yes, to set the sequential specification for this queue, and to fasten the verification process by providing the state equivalency relation on the queue. So please, here I think we can give some time to implement this task. Yes. Okay, Dmitry, what do you think What do you think of verification? Do people ask something about details of verification? Because I think that's rather complicated.
We have some chat about instrumentation, but I think it's too complicated to the moment. It may be discuss it later.
Okay.
About the verification, I maybe missed how we save the state if we don't provide specific extractor.
How we state if we don't provide.
If we implemented just equals and hash code, how we save the state for comparison?
So these then their code every time we. So if we have implemented equals and hash code methods, what happens then, right?
Yeah.
So they will be called every time. So if we are making a transition from one state of the data structure via some method, we get to another state, and we call these equals and hash code methods to find out whether there is already a state. So internally, this label transition system is stored like a map from the state of a data structure, the state that is.
Okay, and how we saving the state? Does it need to be clonable, or how we copy the structure? To compare the states.
So I guess the answer is how we store it, how we store these states internally. So we store them in a map from the object to the list of operations that lead to this object. So we if we go from one state to another, executing some operation, then we just check if we already have this state in the map of states, and here equals and hash code are called.
Yeah, okay, but I don't know. Maybe we should discuss it later. What if you have some unknown list or queue? How you get its current state to the map, so it should not be mutated after applying new operations. How do you copy the structure if you didn't provide extractor?
So I guess we have a list of operations that lead to this state and we can reproduce it, and we can reproduce this state from the initial state.
You're reconstructing it by path from the initial state every time. Okay.
Yeah.
Okay.
So I guess we can. If somebody followed the task, then we can look at it and see what we've done for the concurrent queue. For the concurrent queue, we could provide the sequential implementation and set it in the option for model checking test. And that's exactly what we wanted to do, and we have provided the state equivalency relation on the sequential implementation. We just extended the verify state class and overrided the extract state function. So that was a high-level overview of the verification process, and then we have a section about blocking data structures. Maybe it would be more interesting to discuss some questions from the chat, if there are any. Because the following section touches specifically support of blocking data structures in Kotlin, those suspend functions. Maybe if there are some good questions from the chat, we may discuss them here.
Well, for the moment, we have complicated questions about checking against various hardware architectures like ARM using module verification, but it would be a very long discussion, I suppose, if we dive into the details, because it's talking about weak memory models. So.
Okay. Oh, and I see that Alexei Shapilov has joined the chat. Cool.
Yeah.
And that's why I don't. Okay. So maybe I then I will continue to talk about blocking data structures then, right?
Okay.
So I can say that Lincheck supports testing of blocking data structures from implemented via suspending functions from Kotlin language, and it's better to have some background context to understand that. But the simple examples of such data structures from Kotlin coroutines are like channels, mutexes, flows, etc. You can read more on this in the coroutines guide later. But now I'll show you the simple example of the primitive of the main communication concurrent communication primitive. That is a rendezvous channel. It has two operations implemented, two operations defined. They are send and receive functions. Let's see how it works. How blocking data structures work. So imagine that we have two clients that we have some channel. We have some channel with tasks. That is a rendezvous channel. So here we do not have any buffer. That's just a meeting point of a client and a worker, of the thread that sends values and of the thread that receives values. So the client may the clients send tasks to this channel, and the worker processes them somehow. So imagine that the execution starts with a worker. The worker asks if there are any tasks in the channel provided, and calls receive on the tasks channel. There are no tasks. There are no any waiting tasks in the channel yet. So the worker suspends here and works and loops here, waiting. Not loops. It just suspends here, waiting when some task will be provided in the channel. Then imagine that so some client comes here and provide and send a task to the channel. Then when some task is sent to the channel, the worker is being woken up, woken up, and the rendezvous occurs. So the worker resumes and starts to process a task that was provided by client 1. While the worker is processing a task, the second client sent another task to the channel, but there is no one to process this task. The worker is still busy, so client 2 suspends and waits till the moment when worker will be ready to use this to take this task and process it. When the worker is done with processing of the previous task, here the second client and the worker occur to make a rendezvous again, and that's how this communication primitive works. So this the problem with testing these blocking data structures is that if we have a concurrent execution of send and receive methods, then you cannot find any sequential execution that will provide you cannot find any sequential execution here, because these methods are blocking. So if you call at first send and then receive, then this execution will be blocked on send, and vice versa. So there is a problem. There is a problem in testing. These data structures the way that we've seen in the non-blocking data structures before. So what we can do about this? Actually, we can split the receive operation. We can split the receive operation into two parts. The part before suspend, when the receiver registers itself as a waiter for some task, and then the task after suspend, when it is resumed by the thread that has sent this thread a task, and so we can name the first part as request, and the second part is follow up, and here we come to the fact that this operation split is performed according to the formalism provided in the. This split is actually the same as performed in dual data structures formalism. Dual data structure formalism that you can read more about in the article that I've pinned below. So now when we split, now if we have splitted our operation into two parts, we can find a sequential execution. So at first the second thread registers its request, then we send value, and then we get the follow up. I will not dive into details on how this is performed, how verification of these blocking data structures is performed. There is a talk by Nikita Koval on Hydra 2019, I guess, where he tells all the details on this process. But I'll just tell you the practical part. And we see that if you have an implementation of the algorithm with some suspend functions, then then writing a test to this structure is pretty much the same as we've done before. The only thing that you should do is mark the corresponding test operations that are delegated to suspend functions with suspend modifier 2, and this will work. Okay. What I want you to show is this working test for the rendezvous channel that you can find in the branch 8.1 rendezvous channel. That's pretty simple. There we are just. Yes, I'm going to this branch too. Here we're just implementing test operations called send and receive, and you can run the test and ensure that it passes successfully. Further, I'd like to tell about buffered channel and give a task on writing a test for buffered channel. But on the other hand, we have only 5 minutes left, and this may be rather difficult. So maybe I will skip the buffered channel part, and I will give the final task of this workshop, and then we will discuss some conclusions maybe, and what we have learned. So I guess it would be interesting to what? Okay, the final task as the final task of the workshop, I want you to write a Lincheck test for the data structure from the Java standard library that is called concurrent linking DEC. There is a known non-linearizability in this data structure, and you can actually reveal it using Lincheck. I'd like you to go to the branch 9.1 final task, and there you will find nothing but an empty class. I want you to write this test from scratch. What you need is to declare operations defined. Operations defined in the concurrent linked DEC for concurrent execution, mark them with operation annotation like we've done in all the previous tasks, and run a model checking test, for example, and see if it fails. After our question section, I guess I will push the branch with a solution, and yeah, if you have some trouble finding the bug in the concurrent linking DEC, then you will be able to run my test from the solution branch and ensure that it actually fails and finds a bug. I guess I'm done on this point, and we can go to make conclusions, maybe to the workshop. Dmitry, please tell me what's happening in the chat. I've been having some trouble.
We have some small questions. What's the difference of Lincheck for Kotlin and for Java? I don't know exactly. I didn't know we have two versions.
And we don't have two versions. Like there's no difference in Lincheck for Kotlin and Java. Like there's no difference in Lincheck for any JVM.
Maybe Michael mentioned the old version which was provided in the DevExperts repository, but it's just older Lincheck, which was started with Java.
Yes. Now the version is 2.14. I guess it's much further than those old versions. Yeah.
It leaves us at least 3 years ahead of development.
So we have 2 minutes left, and I don't know. And now we're going to join the question section. And what's the difference with the question section with the questions from the chat, from the Telegram chat now?
Everybody can join you through Zoom.
Through Zoom? Oh,
yeah.
Wow. Okay. I don't have Zoom on my laptop.
In a different environment.
Probably you should install it.
Probably. No.
Or probably you could use the web browser version.
Probably I can use your laptop. Vitaly, are you going to join our question section?
No, I'm not.
No, that's not cool.
Yeah. So I'm kinda trying to finish today.
I suppose Nikita will join.
Yeah, I hope Nikita will join, so you will be not.
Oh, that would be great. That would be great if Nikita joins us.
Yeah, so thank you very much for coming to our session. I think we have only 1 minute left, so let's thank Maria for her excellent talk, her excellent workshop on Lincheck, where she talked about everything what is done in the Lincheck, except for the bounded
buffered channels,
buffered
but
channels, yeah.
no, right.
But it's a little bit complicated, right?
Yes, yes.
So, and thank you very much, Dmitry, that you spend your time
My
on
pleasure.
monitoring the questions and like keeping interactions with Maria, because I'm pretty sure that for Maria it wasn't easy to do it without the real persons
Yes, it is.
in front of her. Okay, so thank you very much, everybody, and we will see you in the closing ceremony of today's day, where we will wrap up with everything what happened there.
Okay, thank you. Thank you, Vitaly.
Okay.